Hi everyone, I'm Shantanu Vyas, and this is a video presentation of our paper titled Con-Struct, where we explore the use of vision language models as reflective thinking partners during complex tasks such as structure design. My collaborators for this work are Suryapavan Cheruku and Dr. Vinayak Krishnamurthy. So, to begin this presentation, I'll first talk about the motivation behind our work. AI has been actively shaping domains of engineering for the last decade or so, from design and simulation to manufacturing. But until recently, it was mostly being used by domain experts or researchers. Now, with generative AI and natural language interaction, the barrier to entry has dropped dramatically. And this shift makes it critical to understand how this new age of AI impacts human AI collaboration while still maintaining human agency in problem solving tasks. Now, human AI collaboration has been studied quite a bit in the past, from analyzing sketch based tools to conversational mind mapping systems. But recent advances in large language models have kind of transformed this field. There's a lot of recent research that integrates LLMs into various engineering tasks, from understanding complex systems to generating creative ideas. But alongside these benefits, there are also negative aspects to this, where there have been studies that show that generative AI tools reduce critical thinking skills and lead to over reliance. So, our goal in this work is to address this gap of understanding of how we can design AI driven workflows that can actively foster reflection and critical thinking in complex tasks. So, to study this, we take inspiration from prior works that use a gamified approach towards improving intuition in areas such as topology optimization. However, this was before the conversational AI phase. So, to integrate the conversational bit, what we did was we built our own design workflow that lets users interactively create structures to meet specific objectives and at the same time interact with an AI agent that is powered by vision language models that are specifically tasked to act as reflective thinking partners. We then evaluate this workflow through a between subject study with 24 participants. So what I'll do now is I'll dive a little deeper into the design of the workflow and the conversational framework itself. So I'll start with the problem context. We chose a structure design task because it's complex enough to require reasoning about concepts such as load paths and material usage as well as deformation, but yet remains visually intuitive. Right? Prior works have also utilized this context to study human AI collaboration. Now, to make the problem more approachable, we focus on 2D structures. And for interactivity, we adopt a graph-based representation of the structures. So let's take an example of this particular structure. We start by identifying nodes as circular primitives and then connecting them with edges by creating a graph using Delaunay triangulation, which is useful because it avoids degenerate or overlapping edges. We then compute the convex hull between the connected nodes to form the truss elements, giving us a complete structure. Now let's take a look at how we can manipulate the graph and therefore the structure to create different variations of the structure. So we start with the template as it ensures that every user begins from the same starting point. From there, users can add new nodes anywhere within the design region, and the graph automatically updates in real time. Nodes can also be moved around, which again recomputes the graph, and the user can adjust the amount of material at a node by scaling it up or down, which also impacts the connected truss elements. Users also have the ability to fill closed cycles with material. And for direct material removal, users can delete nodes as well as delete specific edges. So these options give users fine-grained control over the design of their structure. And since this is a structure design task, we gave users two clear objectives. The first is to keep the material usage within a set limit, and the second is to keep the deformation value of the structure below a target value. Meeting both of these objectives makes it a non-trivial multi-objective problem. For constraints, we set the design domain and we predefine the fixed supports and applied loads for each of the tasks beforehand. And with that, I'll now focus on the design of our conversation framework. So we first start by identifying two ways that the users and the AI agents can interact. So the first is user-initiated conversations, where the user is asking LLMs for suggestions, explanations, and hints. That is something that we are all used to. And the second is AI-initiated conversations, where the agent poses reflective questions during the problem-solving process. So this raises a key challenge. How do we ensure these conversations between the agent and the user stay contextually relevant, and whether the agent suggestions are useful and their questions whether they are appropriate? Right? So to address this, we designed a conversation framework that is built around the concept of contextual channels, which I'll explain through an example. So this is a web-based application that we developed in Unity. It integrates OpenAI's GPT-4o models as our VLMs, and it also runs an SFE PI-based FEA analysis of the structure in the backend through a cloud-based Python script. As a user makes changes to their structure, they get real-time feedback on their design objectives that they can see on the top right. Now let's say this particular user is making changes but doesn't know how to reduce their formation to meet the objectives. So they ask the AI agent for help. Right. So the way a conversation framework tackles this is through a multi-prompt approach. We start off with a system prompt where we provided contextual information about the task that the user is completing, the constraints of the problem, and so on, along with the role of the agent. What this does is it sets the general context for the user-AI conversations. The next step in our framework is to create an in-depth analysis of the user structure, and this is done through the analysis prompt. For this, we provide the prompt with multimodal contextual data, which includes the visual snapshots of the current structure, the underlying graph representation, historical information of previous iterations, evaluation signals including the stress distribution plots that is obtained from the FEA analysis, and finally the target reference, which is obtained through the topology optimization of the given constraints. The idea is to use this rich contextual information to create a detailed report which can be used by the agent to provide a relevant response to the user. So let's take a look at an example of how it uses the evaluation signals. So over here, it identifies regions of high stress and the potential reasons for increase in deformation. Here's another example where it compares the user-generated structure to the target reference. It then curates all of this information into a detailed analysis report, which is then used by the agent to provide a contextually relevant response to the user that is easy to read and understand. We follow a very similar approach for the agent-initiated conversation, which is currently triggered on a rule-based system every 2 minutes since the last conversation. But instead of suggestions, it uses the report to pose relevant questions to make users think more critically about their design. So all this put together forms our Con-Struct workflow. Now to evaluate this workflow, we conducted a between-subject-user study. So in this section, I'll talk about the study objectives, study design, as well as our findings. So we had 4 main objectives for conducting the study, where we wanted to understand the impact that our Con-Struct workflow had on the user's design outcomes, on their design processes and the strategies that they used, the kind of conversations they were having with the AI agent, and its impact on their cognitive load and engagement with the task. So to study this, we recruited 24 participants with backgrounds in engineering and related fields, and they were randomly assigned to either a control group that was working independently or an experimental group that was working with an AI agent. Each of them completed 2 design tasks. One was a cantilever beam type task, and the other was an L-shaped bracket design task. and their goal was to meet the target max deformation and material objectives. They were given 14 minutes to complete each of these tasks, and after the task, they completed post-study surveys and provided their open-ended feedback. Overall, the study took around 60 to 75 minutes to complete. So with that, let's take a look at some of the results and findings. So these are the final solutions from both groups for task 1. So task 1 proved to be challenging for all the participants, with only one control group participant meeting the objectives. When asked about their approach, they said it was mostly trial and error and they weren't sure why it worked. Now visually, we can see some clear differences between the groups. The control group tended to explore more topologically complex structures, while the experimental group worked with simpler node arrangements with stronger resemblance to the optimal structure. Looking at task 2, this one was generally more favorable for the participants. 6 in the control group and 3 in the experimental group met both of the objectives. While more control participants did achieve both the objectives, every experimental group participant met at least one objective, compared to only 2/3 doing so in the control group. And similar to task 1, the experimental group's designs tend to align more closely with the optimal solution. Now, if you look at the design process, we start to see why the outputs differed. So the control group spent significantly more time and iterations in their designs, while the experimental group spent part of their time in conversation with the AI agent. And even when we remove the conversation time and focus only on active design time, the experimental group made fewer changes per minute, which suggests that they were thinking more deliberately and purposefully about their approach. This is further supported by their use of features such as restarts and undos, which the control group used significantly more often. Now, looking at the conversational dynamics, we saw a good balance between users asking for suggestions and the agent posing reflective questions. And to understand the underlying themes in their conversations, we carried out a thematic analysis, which highlighted some of the core structural concepts such as weight distribution and load transfer that drove the discussions between the users and the AI agent. Now, to see an example of a user-initiated conversation, we look at how participant 3 asked the agent how they could reduce material, to which the agent suggested looking at regions around certain nodes like 0 and 3, which had lower stress. It recommended trimming material there or moving the nodes toward the central load paths. The user acted on this by moving node 3, which reduced material usage by about 5%. Here's an example of an agent-initiated conversation, where the agent identifies that a node has been deleted and asks how it impacted material and stress distribution. To which the user mentions that the deleted node did not effectively transfer the load to the fixed supports. Now, moving on to the results from the post-study surveys, the experimental group reported significantly lower extraneous cognitive load, which is desirable. The AI agent likely helped with this by keeping their attention on the relevant aspects of their design tasks. In terms of engagement, the control group found the task more difficult and less rewarding compared to the experimental group, highlighting the benefits that the AI agent had on keeping the users more engaged in the task. Finally, we also gathered user feedback, where most of the control group participants mentioned that they would have liked some help during the design process, whereas the experimental group found the agent helpful and insightful and felt that it helped them reflect on the problem better. In terms of critical feedback, some users did want the agent to be more specific and quicker in its responses. So with that, I'll wrap up this presentation with some of our limitations and future work. So first, the shorter task duration limited our ability to capture how conversations with the AI affected deeper understanding and meaningful differences in final solutions, which could be explored in longitudinal studies. Second, since LLMs and VLMs can hallucinate or misinterpret inputs, we saw occasional mistakes in interpreting visual context. This could be improved with techniques like future prompting or fine-tuning. For future work, we are exploring how changes to the level of contextual information might affect both the design process and the nature of reflective conversations. We also want to experiment with different modes and timing of AI intervention. For example, using voice or visual cues in the tool, proactively explaining design drawbacks, or even detecting moments of user frustration through physiological signals and stepping in at just the right time. So there are quite a few interesting questions and opportunities to explore. But for now, I'll conclude this video presentation. Thank you so much for watching. And for more details about our work, please do read our full paper and feel free to reach out to us with your questions.